Have you ever stopped to think about it? From the planets whirling through space to the very device you're watching this on, pretty much everything is in motion, all the time. But how do we actually talk about that? How do we describe it? Well, today, we're unlocking the physics of how things move. All right, let's dive in.
So, think about this for a second. You've got a cheetah just exploding across the savannah, an apple just letting go from a branch, and you just walking down the street. I mean, they seem like three totally different things, right? But believe it or not, they are all linked by one single fundamental concept.
Yep, you got it. They're all in motion. But, just saying something is moving is kind of like saying a song has notes. It's true, sure, but it doesn't really tell you the whole story. Physics gives us the precise words, the vocabulary to describe exactly how things move. And that is exactly what we are going to unpack right now.
So where do we even begin? Well, it all starts with a question that sounds simple, but really isn't. To understand what's moving, you first have to agree on what's standing still. And that, it turns out, is a much bigger puzzle than you might think.
This is what we call a reference point. I mean, right now, you probably feel like you're sitting perfectly still, right? And relative to the screen in front of you, you are. But what if we change our reference point to the sun? Then you are hurtling through space at almost 70,000 miles an hour. So the big takeaway is this: all motion is relative. And this idea, this is the very seed that eventually grew into Einstein's theory of relativity. It is a huge, huge concept. Okay, so we've got our reference point. Now let's talk about the journey itself. It turns out there are two really important ways to measure it, and even though they sound similar, they could not be more different. Think of it like this. Imagine you run one full lap around a 400-meter track, and you end up right back where you started. What's your distance? Easy, 400 meters. But what's your displacement? It's zero, a big fat zero. Why? Because you ended up in the exact same spot you started. You haven't actually been displaced at all. Distance is the easy one. It's that number on your fitness tracker after a long walk. It counts every single step, every twist and turn. It's just a number, a quantity. In physics, we call that a scalar. But displacement is different. It's the as the crow flies path. It has a number, sure, just like distance, but it also has something absolutely crucial, a direction. You didn't just go 500 meters, you went 500 meters north. That little bit of extra information, that direction, is what makes it a vector. And trust me, in physics, direction is everything. So, we get the path now. Let's ask a new question. How fast are we moving along that path? As soon as we add the idea of time into the mix, we get our next two key concepts: speed and velocity. I bet you're starting to see a pattern here, right? It's the exact same idea we just talked about. One of them is just a number, and the other one includes a direction. Speed is our scalar, and you guessed it, velocity is our vector.
Speed is super simple. It's what the speedometer in your car tells you, 60 miles per hour. That's it. It has no idea if you're going north, south, east, or west. It's just the total distance you've covered divided by the time it took to do it.
Velocity, then, is like having your speedometer and a compass working together. It's not just 60 miles per hour. It's 60 miles per hour due east. See the difference? And it's calculated using displacement, not distance. This is why two cars can have the exact same speed, but completely different velocities if they're just heading in opposite directions.
But let's be real. In our everyday lives, we almost never move at a constant velocity. We speed up, we slow down, we turn corners. So what do we call that change? Well, that's where our next big concept comes in: acceleration.
This is the classic example everyone uses because it's perfect. Picture a car stopped at a red light. The light turns green, you hit the gas, your velocity is changing over time. And that rate of change is what we call acceleration. It really is this simple. You have a starting velocity, 0. You have an ending velocity, 60. Acceleration is just the measure of how quickly you make that change. A fancy sports car and a minivan can both go from 0 to 60, but that sports car is going to do it a whole lot faster. It has a much, much higher acceleration.
Okay, now this is where it gets really, really interesting because we're about to clear up a huge misconception. Most of us think acceleration just means speeding up, but hitting the brakes? That's also acceleration. It's just negative acceleration. And here's the real mind bender. Taking a turn at a perfectly constant speed is also a form of acceleration. Why? Well, because your direction is changing. And if your direction is changing, your velocity is changing. And remember, any change in velocity is, by definition, acceleration.
So, we've got all these pieces now, right? Displacement, velocity, acceleration, time. How do we get them to work together? With a few beautiful, elegant equations. Now, don't let the letters and symbols freak you out. Seriously, think of these as the master keys in our physics toolkit. They let us predict the motion of pretty much anything.
This first one is a true classic. It basically says that your final velocity, that's v, is just your starting velocity, u, plus your acceleration, a, multiplied by how much time has passed, t. So if you know how you started and how you're changing, you can predict exactly how you'll end up. Pretty cool, huh?
All right, what if you want to know how far you've gone? This is the equation for you. This lets you calculate your displacement, s, just by using your initial velocity, the time, and your acceleration. It's incredibly powerful.
In this last one, okay, this one's my favorite. This is like your secret weapon for when you don't know how much time has passed. As long as you know the acceleration and how far you've gone, you can figure out the change in velocity. No stopwatch needed.
Wow, that was a lot, I know. But here's the cool part. It all connects together beautifully. So let's take a breath and put everything onto one single summary slide, just to really lock it all in. Okay, let's nail this down. Distance, that's the total path. It's a scalar. Displacement, that's the shortcut from start to finish. It's a vector. Speed, simply how fast. Velocity, how fast and in what direction. And finally, acceleration, any change in that velocity, speeding up, slowing down, or even just turning a corner. See, it all fits.
And that's the real power of what we just did. You started with a simple idea, things are moving. But now you have a precise language and a powerful set of tools to describe the universe in motion. You're literally seeing the world through the eyes of a physicist.
So, I'll leave you with a final thought to chew on. We know all motion is relative, right? A car moves relative to the road. But what does the Earth move relative to? Is there an ultimate still point somewhere out there in the universe? Now that is a question that takes us to some really, really interesting places. Keep asking questions. Thanks for exploring with me today.